Welcome to the Math Record. Today we'll be learning about different types of charts and tables. This video will cover Chapter 1, Part 2 of our statistics class. In our previous video, we introduced the concept of categorical and quantitative variables. So there's two types of variables, they're categorical and quantitative. In this video, we're going to be learning how to represent each of these variables. Let's start with categorical variables. In categorical variables, the first thing that they would most likely teach would be frequency tables. These are tables that record the total of each category. So it would be like you have a chart, and you have let's say colors and the amount of people that like that color. You have red, blue, green. You have 5 to 1. That's a frequency table. And instead of using amounts, the next chart that we use is called a relative frequency table. Sorry, relative frequency, FRE table. Okay. So instead of so we have the chart back again. We have colors and we have the amount, right? So we have red, blue, green, and let's say it was 2, 3, and 5, right? Instead of saying it's 2, 3, and 5, you add all these together, so that's 10 in total. So it's going to be out of 10. So it's going to be now in percentages. That's what a relative frequency table is. Instead of using the actual amount, you're going to be in percentages. So this would be considered a frequency table. This is a relative frequency table. So the red, blue, green, it will be 2 divided by 10, which is going to be 1/5, which is just 20%. Or blue, which is 3 divided by 10, which is 30%, or 0.3, and 5 divided by 10 is 0.5, right? So they should add up to 1. In the amounts, they should add up to some kind of number. In percentage, they should always add up to 1. Because 1 means 100%, and you can't go over 100%. A different type of graph would be bar charts. I mean, bar charts. This chart shows the distribution of each category. I'm pretty sure everyone's familiar with this, but if you don't know, it's basically let's say you have some kind of variable, I don't know, like colors again, and then people like red, and this one's blue. Oops, sorry, blue and green, you know, and and then you make a scale on the Y, so you make the amounts. So you have a 2 here, 4, 6, etc. So this one will be 2 because right here is at 2. Right here is 4. This one's 6, so it's a little bit below it, so it's at 5. So that's how you do a bar chart. And similar to how a frequency table has a relative frequency table that does it with percentages, a bar chart has a relative frequency bar chart. I'll just write it as relative frequency bar chart. So it just basically shows, it's just the percentage version of a bar chart. So as our example had, we have colors, we have amounts, and we have red, blue, and green, right? So you're gonna split into parts. So remember our example, which is 2, 3, 5. So now we have 0.2, 0.4. Let me not use that. 0.2, 0.4, 0.6, 0.8. You know. So red is 0.2, blue is 0.3, and green is a 0.5. You know. So basically like this. and all these charts should add up to 1. Most likely, you're gonna never use relative frequency bar charts, but the ones that you're really most likely to use is frequency tables, relative frequency tables. Those could be interchanged usually, because instead of looking at the amount, which is sometimes kind of hard to see, it's easier to look at percentages. And but it could also vice versa, because you want to look at more amounts to be more precise. And then there's bar charts, which is just relatively really good all the time to like show like and compare data. Relative frequency, it's also good, but it's not used as often because bar charts could basically do the same thing. But now with percentages, it's kind of a little bit hard to like know the exact amount. But it's still safe to use sometimes. Next up, we have pie charts. So instead of putting everything in like rectangles for like bar charts, now we're gonna put it in a circle. So let's say you had like red is like 2, blue is 3, and green is like 5, right? So half of this, because it's out of 10, so 2 plus 3 plus 5 is 10. So half of this would be green. And then 2 of the 3, so we have 5 remaining, so 2/5 of this is red. So we can have something like right here is red, and this is blue, right? So it's basically, so there's 2 of here, 3 of here, and 5 of here, which makes sense because the size of the area represents how much it is out of, and you can add more variables. So if you add like a purple, right, and then you could basically put, sorry, purple, which you could basically put like 4. You could basically just like think about it, and then you have 3 plus 2, that's 5, that's 10, that's 14. So 5 will be a little less than a half. So it'll be like, you have like the center of the circle, right? So a little less than half. Let's say like right here is green. And then blue is like rough, almost about the same size. I mean, purple is roughly about the same size with 4. So this is 5, this is 4. And then you have blue, which is just a little less than that. And then you have red. So this is 2 and this is 3. Basically like that. I'm pretty sure everyone's pretty familiar with with pie charts. So I won't be going too much about that. This one where you're gonna be most likely to use mostly all the time. It's called contingent, conti- sorry, contingency. Sorry, I forgot the N. No wonder I can say it. Contingency tables. These are basically frequency tables. Like remember, there's you have like color and amounts. So you have R, B, G, and then 2, 3, 5, right? Now instead for a contingency table, now there's gonna be 2 variables. So let's say you have something like a chart like this. We split it here. We split it right here. So we could have like a something like yes, no, and then red and blue, and then you have like 2, 3, 4, 5, right? So there's 2 variables saying yes or no, so let's call this choice. And we have color, which is red or blue. So this would become a contingency table because there's 2 variables, choice and color, and each of these have like some kind of number basically. So it's basically just a frequency table with 2 variables. For this one, there's 2 types that we could write it as. There is a marginal distribution. Sorry, distribution. Okay. A marginal distribution is basically like the frequency table in relation to like the relative frequency table. This one would be the one with total, so basically like this, where you have 2, 3, 2, 4, 3, and 5. And then you have something called a conditional distribution. This one would show the percentages basically. So you have like 2, 3, 2, 4. Actually, let's change these numbers. Let's say 1, 2, 3, 4. So 1 plus 2 plus 3 plus 4 is 10. So this would be 0.1. This would be 0.2. This would be 0.4, and this would be point 0.3. You know. So it's now gonna be in percentages, and always with percentages, you're gonna have it add up to 1. Like each of those boxes will add up to 1. And finally, the last thing in categorical, we're gonna be learning about is segmented bar charts. Bar charts. Okay. So these are basically just charts that show the percentage distribution between like bar charts. So basically, this is like imagine everything is out of a percentage of 1, but it's only one bar chart, right? So let's say you have one person, let's say some kind of boy, right? And let's say he has to choose what's his favorite color, like RGB, and he likes red like 50% of the time, right? And then he likes blue and green about equally, about like 25% of the time. And then you have like let's say a girl, right? And you have it's also out of 1 because it's always out of 1 because it's out of 100%. So let's say she likes red, blue, and green about equally all the time. So each of them is about 33%, right? So it's got to be written like this. So this would be 33%, this would be 33, this would be 33. And red here would be 50, here would be 25 for blue, and this will all be 25 for green. What we usually use these segmented bar charts is to determine if these like data are like between like two variables are different. So our variable is like gender, which is boy or girl. So basically we're trying to see if the red are basically the same, the blue are basically the same, the green is basically the same, and overall is it basically the same. Because based on these numbers, you might say there could be a difference, or there couldn't be a difference, because you could say 25 to 33 is only just 8% difference, and then 50% to like 33 is like 17% difference, which seems like a big amount, or maybe it isn't. So based on these bar charts, it just basically tells you it gives you evidence to show that like some variables like might differ between each other. Now let's move on to quantitative variables. A quantitative, right? Sorry, that's not I there. That's an A. This is basically any charts and tables that like show you how to like graph like actual numerical answers. So let's start with the basic one, which is stem and leaf. It's usually referred to as stem and leaf plot. Okay. So these basically show individual values in a chart-like way. So imagine you have something like you have 1. This is 1, 1, 2, 3, 4, 5. Actually, let's say 2 here. You have 5, 6, 7, 9, 3, and then you have 1, 2, 2, like 3 or something. Now, basically, what this means is that you have to always write a key. Basically, a key would be like if you have 1, and then the vertical line, like this line right here, and then you have another 1, and you have to write it as equals to 11, right? So you always have to write a key just so you can specify what it is. Everything has to be in context, always in context. So so basically how you read this is that be like this would be 1 is 11. This one would make it another 11. This would be 12. This would be 13. This would be 14. Starting with the 2, right here is a 25, then 26, then 27, then 29. And then you have 31, 32, 32, 33. You see how this works? This would just be like, it shows individual values, but instead of writing like the tens digit multiple times, this is basically how you're going to write it. There's also like, if you want to write like hundreds digit, you could just like write 32 and 1. And that's why you always need to have a key, because then you can have like 32/1 is equal to 321. So you always have to write a key. Usually it's just one value on the right side and some value on the left side. Because you can't put like 3212 to make it 32,112. Because then like what happens if you put another one? Because then people get confused. Because is that a 4 digit? Like how do you make a 4 digit from 3, 2, and 3? Like sometimes you just have with the key it'll still be kind of confusing. So you only put one value ever in like the right, and whatever value you want to put in the left, you just make a key to like find out what it basically means. And next up we have dot plots. Dot plots. This basically just shows the amount of dots equal to the amount in the data. So let's say based on like our chart, right? We have like red and like color and amount. So you have red, blue, so you have like and green. We have 2, 3, and 5, right? Then basically we're gonna have red, blue, green, um, and you could basically say like 1, 2, 2 dots for red, 3 dots for blue, and 5 dots for like green. It's basically just that simple. You for this type of like graph chart ish, you won't be using this as much as the one that we're gonna be showing right now, which is gonna be called as histograms. Histograms just show the distribution between like quantitative variables. So instead of using the dots, you're actually gonna be using rectangles. So let's say you have like a scale, some kind of scale, right? This is 0, this is 1, this is 2, that's 3, that's 4, that's a 5. And this is the whatever the x variable is, and then you have the y variable. So you have like 1, 2, 3, 4, right? So let's say you have the amount of numbers between 0 and 1 is 1, and the amount of 1 and 2 is like 0, and then 2 and 3 is like 2, and then this, and then like baby back to 1. So basically it does like a without using dots, we're gonna actually be using like rectangles for the graph. We basically use these charts a lot just to show if like the model is gonna become normal. So a normal model would basically be like if it looks like this, which each side here, this side is symmetrical, and there's basically one peak, right? So this graph is basically kind of like a quadratic, except it doesn't go through the x-axis, so it's always going to become positive, but it gets really, really small in both sides. So basically, we use a histogram to find out if it kind of looks like a normal model. This will be explained further in our future videos of why this is important. And finally, we have relative frequency histograms. Okay. These basically show the percentage distribution of quantitative variables. So like how the histogram use like actual bar charts to show the amount. Anything with relative in its name is always with percentages. So let's say we have 0, 1, 2, 3, 4, and then you have like 0.2, 0.4, 0.6, and 0.8. And you have 20% here, you have 40% here, and you have 20% here, and you have 20% here. right? So this adds up to 100% because 20 plus 20 plus 20 plus 40 is 100%. So that would just be a relative frequency histogram. You most likely won't be using this, but the one that you're going to be most likely to use constantly is probably stem and leaf to show individual numbers, because then you don't have to write a lot of numbers like multiple times. Instead, you could just write like a general idea and use a key. And then there's the histogram, which you're going to use a lot of in this class. Going back to the normal model, in general, there's three ways you have to describe it. You have to describe the shape, you have to describe the center, and you have to describe the spread. So the shape is basically like how does it look, but the usual way that we do this is that we describe the amount of peaks in there. So like a normal model, right? You have something like this, you have one peak right here, right? And then if we have something like this, right, we have two peaks. So if we draw this in like a histogram way, because usually you're gonna be looking at histograms and how this looks, you're gonna have like graphs like these, and then you have like, right, you're gonna have two peaks. But sometimes it's not as obvious, and you put something like right here, and they put something like right here, and right here, and then here, and this one's just slightly ahead. You don't call these three peaks, right? Because this thing is like really close to here, and this one's really close to here. You might just call this a just one peak. Sometimes you can argue it, sometimes you can't. Sometimes it is usually not as confusing all the time because like it's sometimes kind of obvious, but usually when those cases happen, you could argue either way. So to describe those, the amount of peaks, if you have let's just delete this because we're gonna just be talking about shape for now. If you have 0 peaks, it's gonna be called as uniform, or if it generally like looks like pretty equal on all sides. So you have something like this the entire time, right? For each category. So this is 1, 2, 3, 4, 5, 6 categories, and they each have like an equal amount. Or if it's like something like this, then right, you go back up, go down, right, and it looks like it's pretty uniform, even though like some of them are a little bit higher than the others. You would just call it uniform. And if they have one peak, which is like the normal model, it's gonna be called unimodal. Because the way you describe peaks in statistics is that you call them modes. The number of modes. So the modes is basically the same thing as peaks. And then you can have two, which you could say is bimodal, because bi means two. And then if you have three or more, we usually just call it multimodal, because there's a lot of them. And other than this, another way we describe graphs is we either call it symmetric or we're gonna call it cube, like going back to the normal model, right? Basically, a normal model has this side is equal to this side, so it's symmetrical. So you like have this as a paper and you fold it around this axis, then basically it's gonna fold onto itself perfectly, usually perfectly. This is often called symmetric, right? So any graph that like basically has like an equal left and right side, like basically anywhere, is symmetric. And then a different kind is that we're gonna have skewed. There's only technically two kind of skewed. So if you have like something like this and it goes down, and you're gonna have like something go down here but then goes back up, right? So this one is at the left and this one's at the right, you know? So this at the left, this at the right. So these are gonna be called bell curves, but more specifically, they're gonna be called skewed. So how do you name this? You're gonna call this skewed to the right. This graph right here. Because how you name this is basically really simple. You kind of just look for where the tail is. So this thing right here is referred to as the tail. So same case here, this would be referred to as the tail. So basically from the tail, wherever it's going is how you're gonna name it. So okay, so basically, since this graph is the tail is going this direction to the right, then you're gonna call it skew to the right. And you're gonna see this tail right here, which is going to the left, right? So you gotta call it skew to the left, right? So it's basically just that easy to name. Just find out where the tail goes, and then name it based on like where the tail is going. So that is basically for shape. Now we're gonna learn about center. Center is where the data is clustered at. So it's gonna be this is usually described with as the mean or as the median. So mean, you just sum all the numbers in a data set and then divide them by the amount. The amount is usually referred to as n. And then we're gonna have median, which is just the middle number, the middle number that you have to look for. So that's because these are the centers that it logically makes sense where the mean and median is. I mean mean, yeah, mean and median is. And then the third thing you have to look for is spread. There's usually three kind of spreads that you look at. There's the IQR, which is stand for interquartile range. So this is basically if you have a bunch of data and you look at where the 25th percent data is and the 75th percent data is, and you subtract those values together. That's the interquartile range. Okay. And then you have range. Range is basically where the max number is subtracted by the smallest number. So it's the max number minus the minimal number. So let's say let's say you have a data set like 1, 2, 3, 4, 5, right? So the max number would be 5 minus 1 is 4. And if you're looking for IQR, the middle number is 3. So usually how I do is that I see the number is 3, and then I kind of just look for, then I use this side and then this side. So looking for the 25%, this and this 3, so the one in between is 2, so the 25% is at the 2. And now we have the 3 and the 5, so the number between is 4. So the IQR would just be the 75% is the 4 and the 25% is the 2. So it'll be 4 minus 2 is 2. That's the IQR. And that's usually how I do it. Just look for the middle number and then kind of like use your fingers to keep like moving like up, like one down and one up, and then you basically get the middle number for the 25% and the 75. And the last thing that we're gonna teach is standard deviation. This is gonna be a concept that we're gonna use a lot in statistics. So I generally you should probably know how to you should probably learn this like in the internet, like from YouTube or Google, like how to like calculate this because it's a little strange. But there is two types. There's gonna be sample. There's a sample standard deviation and there's a population standard deviation. The difference is kind of stupid. Basically, a sample is basically we have the Euler summation. Euler summation basically just means sum. So the sum of all the numbers of let's say y minus the mean of y, and then square those numbers, and then you divide by n, and then you square root that entire thing. I mean minus 1 for sample. So you have the number of so basically how this works is like, let's say you have like something like 1, 2, and 3, right, as your data. The mean is going to be 1 plus 2 plus 3 divided by 3, which is just 2, because that's 6 divided by 3 is 2. So the mean is 2. So then you have 1 minus 2, which is negative 1. And then 2 minus 2, which is 0. And then 3 minus 2 is 1. And then you're going to square all these numbers. So negative 1 squared is 1, 0 squared is 0, and 1 squared is 1. And then you're going to add these numbers together, which is 2. 1 plus 0 plus 1 is 2. And then you're going to divide by the amount of numbers. The amount of numbers minus 1. So there's 3 numbers. There's 1, 2, 3. And then 3 minus 1 is 2. So then you divide by 1 of each other, and then you take the square root of that remaining, right? So you square root that. So 1 square root 1 is 1. So you have a standard deviation. You have a sample standard deviation of 1, basically. So that is a sample standard deviation. So that's basically how you calculate for spread. It would be just like, where is the data set like differ from the median, and then you only want the positive values. That's why you square it. Because if you have negative 1 and 1, right, they cancel each other out and you have 0, and then you have 0 divided by like 2, and then you square root and it's just gonna be 0. But you can't have a standard deviation of 0, because like, let's because like how I relate this to this is that, like, let's say you have like you're flipping a coin, right? So let's say you get like 2 heads, you flip it twice and you get 2 heads. It's not unlikely that it's gonna get 2 heads, but you expect it to have 1 head and 1 tails. And that's what it means for that standard deviation. Did you have this 1 extra head instead of getting a tails? So, and now you have population standard deviation, which is basically the same concept. It's just the square root of the sum of those numbers, and then those values minus the mean of that value. But instead, you just divide by n instead of n minus 1. So if you want to use a sample standard deviation, you have to minus 1. If you had to use a population, you just divide by n. And that's basically it, because like populations are basically more precise. So instead of like minusing 1, you really don't have to, because for samples you have to minus 1 to get a basically more accurate one. So those are the 3 ways that you're gonna be talk about spread. You usually only have to talk about for shape, center, and spread. You only have to talk for shape. You just have to talk about the amount of peaks, if it's symmetric or it's skewed. For center, you only either talk about mean or median, and for spread, you either talk about IQR range or like standard deviation. You don't have to talk about all of them. Usually, you just talk about one of each. So one of like center and one of spread. And last thing you ever want to mention is in a graph, if there's any of them, is that they're outliers. Because you just want to know if there's like any differences from the data that's extremely weird. Like if we have like a histogram, right? Because usually you're gonna be talk about shape, center, and spread using histograms. Yeah, something like this. And then you have like a point all the way up here. This would be count as the outlier right here. And then you can see like a bunch of points here, and then you maybe like somewhere right here you have the mean or something, right? And then you have like standard deviation, which you're gonna have to calculate, because usually you're gonna have like numbers here as the x-axis and the numbers here as the y-axis, and you're gonna use this to calculate the standard deviation. You're gonna also be using the outlier, but sometimes it's gonna make it a little weird. Like it's gonna be larger than usual. Because if you think about it, like you have a standard deviation. The standard deviation, by definition, means like how much does the values like differ from the mean. Since this value differ from the mean a lot, then basically since this value is so far away, it's gonna make the standard deviation higher. It's like you're adding a bunch of amounts. Then but usually this outliers like don't affect as much. Usually when you have like a really high sample like number. So if you have like you have 50 numbers, right? Compare that to like 100 numbers. If you have 100 numbers, then it's the outlier is not gonna be as much, because based on the equation you have to divide by n or divide by n minus 1, right? So then if you divide by a higher number, it gets smaller. So it usually outliers don't like affect it as much as like if you have a higher sample. But you have a sample like really low, like 10 or 5 or something like that, basically the outlier will affect it a lot, and you should mention it. But even if you do have like high like sample, like a high amount, then you still should talk about it just in case. So which center and spread should you use? Whenever you see any graph that's symmetric, right? We talked about shape, which is symmetric. You're gonna be usually talking about mean and standard deviation, which I usually refer to as SD. And then if it's ever skewed, right? You're gonna be using the median and the IQR or the range. Either of them is fine, because usually sometimes they don't give you some of the information, so you're gonna be using these. But if you could include the mean in the standard deviation is good. Just put everything in context. So explain why the mean is greater than median. Explain why mean is less than the median, or explain why standard deviation is so different from IQR in like a range. So everything should be placed in context so you understand what they're talking about. Like you have like, in my coin example, which I talked about, like a coin which has two heads instead of like one heads and one tails. You could say like the standard deviation is one, because you assume there is one heads and one tails because it logically makes sense if you flip it twice because they have equal chances. Except you get two heads, you have a standard deviation of one. Numerically, that doesn't make sense, but like maybe. But I'm just trying to give you a basic gist of how it like makes sense in my head. And the second to last thing we're gonna learn, we have box and whisker plots. You might have learned this in school or elementary, high school, but basically you're just gonna have like, let's say a graph, and then you're gonna have like something like this and something like this, right? So you're gonna be given a lot of data, and then you're gonna have to, like, when I talked about like the IQR, this would become the IQR right here. Sorry, I couldn't draw the entire thing. But basically this is gonna be at where the 25% is. This is where gonna be the median is. This is the 75% data mark. This is the upper fence. And this is gonna be the lower fence. Sometimes the upper fence could be referred to as the max, and sometimes the lower fence could be referred to as the min. But I'll get to why it's gonna be a little different, because it's gonna be because there's some things, because sometimes you're gonna have outliers, right? And sometimes like the outliers are like the max number, right? But basically it's, you can't constitute them as part of like the data. Well, it is part of the data, but you don't want to put it in the box and whisker chart, because like plot, because the numbers are so unusual that it's sometimes it's referred to as way too big or way too small. So you have these upper fence and lower fence to see if it's generally should be in the data, or is the point just so unusual that's considered as an outlier. So basically how you determine a lower fence or upper fence is that, like, let's say let's delete this for a second. We have like a data set like 1, 2, 3, 4, and then like 10, right? So then you draw like let's put another 10 in here. Actually, actually, we'll just keep it like this. So the median is at 3. So we just, right here we put 3. And then the 25% would be at 2, right? Because this is the middle number and this is the smallest. So the middle is 2. If there's even more numbers, like there's like a 1.5 and a 2.5, then you have a 2 because it's 1, and then 1.5, and then 3, and then 2.5 is 2. You get the idea of how this works. So then you have right here, you have 2, and you have 4 as the 75%, and then you draw the box, basically. So the 25%, the median, and the 75%. And then you have 1, and then you basically have to calculate this. So you have the IQR, which is 4, minus 2, which is 2. So the IQR, which is just this distance, is just 2. So the general rule for calculating the upper fence and the lower fence is the upper fence is equal to the IQR is equal to 1.5 times the IQR plus the 75%. And the lower fence is equal to 1.5 times is equal to the 25% minus the 1.5 times the IQR. So I don't know why they use the IQR. It's just a general idea that you're going to have to be using to calculate the upper fence and the lower fence. So the IQR for us here is 2. So 2 times 1.5 is 3. And 3 plus the 4 is 7. So we're going to have somewhere around 7, right? And then 10 is greater than that 7. Even though it seems like this should be the max and where it should be usually, it's not. It's gonna be an outlier. So it's gonna be somewhere right here, which we're gonna which we're gonna graph as a dot usually. And then 2, and then the IQR, which is 2, multiplied by 1.5 again, which is 3. And then 2, the 25% minus the 3 is -1. So 1 is gonna be in our it's in the data set and it's the smallest amount, so you don't have to go to -1. You're just gonna draw up to 1. So that's how you draw it for like this data set, and that's basically how you do it. There could always be more outliers. So let's say you have a 11, yeah, add one right here. You have a 12, yeah, another one basically. So you basically, when you calculate the upper fence and the lower fence, you're gonna look at the data set and see which like of the data points are like outside, and you're gonna put a dot for each one in like those orders, so like 10, 11, 12, to like to graph as the outlier basically. And that's the basic gist of box and whisker graphs, just to show if like they're outside or not. And the last thing we're gonna be learning is scatter plots. This is very common and used a lot. Um, you might have heard of something like if you have a bunch of points together and you could see that it kind of goes like up. You kind of draw a line there and you call the line of best fit. It's usually called the line of best fit or the regression. So this is what a scatter plot would be using. So if you have a bunch of points, usually you're gonna have to be describing them in calc because I mean not in calc in stats because you're gonna be explaining how it looks in context because everything has to be in context. So you're gonna have to describe its form. So you're gonna be asking if it's linear or if it's not linear, or referred to as non-linear. So it's gonna be either one or the other. Because sometimes maybe the regression line looks something like this, goes down and then goes back up again. So it kind of looks like a quadratic function. So you have to say it's non-linear. Or it has like no pattern at all. So you have something like just like a bunch of random points. Then it's gotta be non-linear because there's no pattern. But if they sorry about that. But if you have something like this, then basically it's gonna be linear. So that's form. You're gonna have to be writing these like actual literally. So you're gonna have to write this with words to explain, to describe. And then you're gonna have direction. Direction is either positive or negative. Or it's gonna be like basically none. Because if you have something like this, the direction is basically this, you can just say it's none. But you have a direction that's like this, positive. And if you have a direction like this, it's basically negative because it's going down. And then you're gonna have strength. Like how close are the data points together, basically. So basically, let's say you have a bunch of points that are really, really clustered together, and it's going up. You're gonna have say it's a strength is strong. But if you have like a strength that's something like this, right? But it's generally going up, then basically you're gonna call it weak. Because even though it is showing that it's going up, like data are so spread out from each other that there's gonna be so much variation. The variation means basically the difference from like basically the mean. So like how it's like changing, how like different like those numbers are from each other. So that is strength. You usually describe it as weak, moderate. So if it's like okay strength, but you can't say it's weak or strong, and they're strong. Okay. And the last one that you might want to talk about, but it's not necessary, is variability. Which is it yeah, let me just delete this. Okay. So last one, call it variability, which usually refer to is the graph like constant or not. If it's constant, if you say it's linear, just write constant because usually that's what the answer is. but sometimes the graph looks something like linear for a while, right? And then it kind of like branches off like this, right? So it looks like linear, but then like for some reason it's going outside. It's gonna be called fanning to the right because like it's going to the right this way, right? And the same case if you have something like, let me just use the same graph. Let me delete some of these points. Okay. So we have something like outside, but then starting getting to like really small, right? So instead of, it goes something like this ish, right? Basically. So except when you're reading a graph, it doesn't look like this. You're supposed to like read it like basically like this, right? So basically, you're gonna be calling this fanning to the left because it's like a really weird scattering out on the left, but then like at this part it gets like really linear. So sometimes you could describe this if you're describing the strength, you could sometimes call it strong or weak. Usually, I just refer to it as moderate because at some point it's really strong, but at some point it's like super weak because of the fanning. And then when you're like describing scatter plots for the x and for the y, for the x, and you usually describe it as the explanatory variable. I would just call it var variable. Okay. And then for the y, it's referred to as the response variable. This would be very important because if you're ever gonna get tested in exams like the AP exam, they're gonna be using explanatory variable and the response variable, and you want to understand which one's your x and which one's your y. And this is basically the general gist of which how you organize it. The response is the y. Because think about it, it's the response, and the one that you want to explain in relation to the y is the explanatory, and that's basically how you're gonna be working with scatter plots. These are most likely used with like experiments, so you can understand like which one's your explanatory and which one's your response. Well, that basically covers everything in this video. So in summary, we learned how to represent categorical and quantitative variables through different charts and graphs. Thanks for watching, and I'll see you at the next math record.